My name is Deech. I live here in St. Louis. I work at Intoximeters. Since today is National Talk Like a Pirate Day, I will be pointing to slides with these. In case the first one breaks, I have the second one down there, because that's important. So today I'm talking about Shen. It's one of the newer entries into the Lisp family, and one of the more interesting ones. So let's just get some syntax out of the way real quick. This is how you define a function in Shen. You start off with define, which is fairly routine, and the name of the function, but all of the arguments are pattern matched, right? So that first pattern match only happens if the second argument is nil. If the second argument is not nil, it just falls through to the second thing. So if I go welcome strange loop nil, it's just going to say welcome to strange loop. If I say welcome strange loop St. Louis, it's going to say welcome to strange loop and St. Louis. So this is not very Lispish, this is very ML-ish, but it's still a Lisp, trust me. It's just got this pattern matching, which is actually really nice. It's also got optional type checking, which you turn on by using the form TC+. It's turned off by default. And you have simple types. So here's a function that checks to see if a number is positive. It takes a number. It outputs a Boolean, as you can tell by this type signature right here. And the body of the function is pretty simple stuff. It just checks to see that x is a number and that x is greater than 0. But note that when you run the function in the normal way, the output actually has a type attached to it. In this case, it's Boolean. So that's pretty simple. But Shen also supports polymorphic types, as in the standard definition of map. So map is a function that takes some A to some B, a list of A's, and outputs a list of B's. In the first case, if the list is empty, it just outputs the empty list. In the second case, it pattern matches against the head of the list, and the bar actually pattern matches against the rest of the list. So XS is pattern matched against the rest of the list. You apply F to the head of the list, and then you recurse on the rest of the list. If you are at all familiar with Haskell or OCaml or any kind of ML, this is a very familiar encoding. So something to note when you are running this function is that Shen supports currying by default. So I don't have to go map lambda x plus 1. I can just go map function plus 1. And also the second thing to note is that the output has type list number. Even though we've said in the type signature that the output is of type list B, the Shen type checker had sort of the intelligence to figure out, even though we didn't tell it we're giving it a list of numbers, that it figured out that a list of numbers is coming out without me telling it anything. By the way, those type signatures up there are mandatory if you have type checking turned on, but only at the top level. You only have to give the type of the actual function itself. You don't have to give the type of each individual thing inside of the function. You can also turn off type checking, and that's the default mode. And in that case, the type signatures are just ignored. You can have them in there, and it's kind of useful for when you have a file full of type-checked functions, and you just want to figure out if some function is working or not. Just turn off type checking, run it. No big deal. So when you run it, in this case, the output is just the value. You don't have a type attached to it. But notice I also snuck in this like weird alternate lambda syntax that Shen has. It's /dot. And the reason they have that is because if you squint at it right, it kind of looks like a lambda. That's it. That's the only reason that's there. You can just use lambda if you don't like that. Yeah.
The Unicode lambda or LAMBDA?
Lambda, LAMBDA, which you can, I guess Emacs can rewrite that to a lambda character for you. Sorry. So that was a crash course on Shen syntax. So some reasons why Shen is a good thing. First of all, optional type checking. It's the language that really made me reconsider my original thinking on optional type checking, and now I think it's actually a good thing if done right. It's also got a very, very flexible type system, and we'll get into that quite a bit more in a second. It's also got not just ML-style pattern matching, but Prolog-style pattern matching, which means that if you use the same wildcard in a pattern twice, it means the same thing. It's equality right there. So if you want to check and see if your two arguments to a function are the same, you just use the same wildcard twice. And you don't have guards or anything like that, and it makes code a lot more concise. It's also got a full Prolog engine, and the reason it has that is because the author needed Prolog to build his type checker and just expose that to the user. It's also got a full parsing engine for the same reason, because the author needed a parser to parse Shen code and just expose that to the user. We'll look at that more in a second. But the best part is it decompiles to this very, very small schemish S-expression-based language called K-lambda. And basically what that means is that Shen is extremely portable. If you can write a scheme interpreter, and if you can provide about 45 primitive functions, like if, and, or, read file, and a few more, you basically have a Shen sitting on top of your platform. So the idea is that, at least the approach that I take with Shen and why I think it's a good idea is, say you have some polyglot project, you have JavaScript, you have Ruby, you have like at least 15 other languages sitting in your enterprise. It's easy to port Shen to all of these different platforms and then encode common data structures and invariants in Shen and test it once. That's the theory anyway. The author calls it a unifying meta language, and I think that's kind of a long way of saying what I just said. So I have a couple of web app demos, really simple stuff. The backend is written in the Shen port of Ruby. The front end is written in the Shen port of JavaScript. It's not important that I use Ruby or JavaScript. What's important is that all the common code is written in Shen, and it's all type checked in Shen. Not type checked, value checked, and type checked. All the checking is done in Shen. So the first demo I have is just a simple username and password form. And if I type in blah-de-blah, it's going to try and send it. Whoops. It's going to complain and say the username must have only letters. And if I type in a bunch of stuff for the password, try to send it, it's going to complain. And you can't see what it says all the way over there, but it's saying it must contain the same number of letters, digits, and one of at least underscore or bang. And all of this validation is being done in Shen. And it's being done both on the JavaScript side and the Ruby side. So if you were to send these as query string parameters with curl, you would get exactly the same message back from the Ruby side without any duplication of code. Okay, so how do we do that? So we have this top-level data structure called model up there. And by the way, the two asterisks surrounding model are sort of this Lisp idiom that means this is a global mutable data variable. I don't know why it's called that, but they're called earmuffs. So just, it's a Lispism. So inside of model, we have a vector. And a vector in Shen is designated with the @v. And inside of the vector, we have two pairs designated by @p. The two pairs represent the two fields, username and password. And aside from the string username and password, we have associated functions to validate the user input of the username and the password. So running a validator basically means taking a key, which is either username or password, iterating through those pairs, finding the validator function, running it on the given value, and then handing that back to the user. The lookup function is very simple, but the only reason I show it is because it uses this idea of Prolog style pattern matching as opposed to ML style pattern matching. So notice here we have a vector and a pair with a key, and we've passed in a key, but the wildcard is exactly the same, so we don't need a guard to check and see if those two things are equal. This first pattern will only fire if those two things are equal, and we just kick out the validator at that point. So parsing. In Shen, parsing, you build a parser using this defcc keyword. It's actually a macro, but yeah. And we're calling the parser alphas. This is to parse the username. We're just parsing only letters at this point. So parsers are delimited by semicolons and into rules. So what this is saying is that if I can parse a letter followed by more input, then go ahead and stick the thing I just parsed into a letter and stick the rest of the stuff that I can parse into a letter. The last rule is saying that if I've reached the last letter, just stick that all into a list, concatenate everything, and hand it back. So a parser is just a simple function. It decompiles to just a straight define. So I can call it a function, and I run the parser using this compile function, which then takes a list of bytes, by the way, not actual characters. So I have to convert the string to a list of bytes, and out comes a list of bytes. But we actually don't care about the parser output. All we care about is the fact that it actually parsed. So we have a function called parses, which takes the parser and the input, compiles the parser, runs the parser on the input, returns true or returns false if an error occurred. So notice we're doing this thing called, we're using this do macro for imperative style programming, and we have this construct called trap error for exceptions. Slightly more interesting is the actual password parser, because notice it had to have equal numbers of letters, numbers, and one of a couple of special characters. So the password parser consists of 4 rules. So if you're parsing the password, you're either looking at a digit, a number, in which case you add a function called addDigit, which I haven't shown you yet to the list. You're either looking at a special character, in which case you add a function called addSpecial to the list, or you're looking at a letter, in which case you add a function called addAlpha. So basically, the thing to take away from this big mess of code is that user input is being translated into functions. So if the user typed in hi 123 bang underscore, that gets translated into a list with function addAlpha for the hi, addDigit for the 1, 2, and 3, and addSpecial for the bang and the underscore. And this is what addAlpha, digit, and special look like. They're just a triple, and all I'm doing is incrementing the right position in that triple. For alpha, it's the first. For digit, it's the second. And for special, it's the third. So Shen has this really handy function called compose, which takes a list of functions, an initial starting value, and just runs it all the way through that list of functions. So hi 1, 2, 3, I guess that should be bang underscore, gets turned into the triple 2, 3, 2 for 2 letters, 3 numbers, and 2 special case characters. And to validate that, you just have this function called validate password, which takes that and does some very simple Boolean operations on it. So in order to call this from the JavaScript side, there's a function called callByName, which takes the Shen function as a string and passes in some values. On the Ruby side, it's just passing a message to an object. Really simple stuff. So that's, in a nutshell, how you, on the high level, how you do sort of common code sharing among multiple tiers, basically. But we really haven't looked at the type system just yet. And to look at the type system, I have a very simple demo also called counter. All this does is increment the counter. So increment the counter. If I put in a negative number, it's going to complain. If I put in anything other than an actual positive number, it's going to complain. So I'm using the type system here to make sure that what I'm inputting is actually a positive number. And to do that, I have about 2 or 3 different functions. So I have a function called string2positive number, which takes something of type readable string and outputs something of type positive number. I have not shown you what readable string or positive number are yet. That is coming up. I have a function called addPositive, which takes 2 positive numbers and outputs a 3rd positive number. And I have the function that we saw before called isPositive that takes a number and outputs a Boolean. So how do we make a data type in Shen? We use the keyword, actually a macro, data type called positive number. And data types are segregated into a bunch of what are called sequents. A sequent means a bunch of conditions that must be true, a bar, and the actual thing that you're trying to prove. That's all they are. The thing above the bar has to be true in order for the thing under the bar to be proven. So what this is telling you is that if I have seen, if I'm looking at a form which is plus xy, and I want to prove that that thing is a positive number, I have to show that x is a positive number, and I have to show that y is a positive number. That's it. That's all there is to it. Actually, that's not it, but that's it for this example. So Shen also has a really amazing feature of the type system called verified types. Now, what this funny looking sequent has is it has no conditions above the bar. That means it's true if the thing under the bar is just matched. What this is saying is that if I see the form is positive x of type verified in the list of assumptions, when I'm trying to prove that x is a positive number, then x is automatically a positive number. What this means in practice is that if I have a function called makePositive, and I have that form is positive x as a where clause on one of the patterns, the type checker will see that form, syntactically match it against this form over here, and just go, okay, he's got some check over there that returns a Boolean. Go ahead and rubber stamp this function as a positive number. This is something that you would use in languages like Haskell or Camel. You would use phantom types to do something like this. So you'd have an empty data type, and if a function passed some check, you would stick that data type on it and that data type designates that it passed. In Shen, you just cut out the middleman and just pattern match on the actual validation function itself. So parsing the digits from the counter is pretty simple. The digits parser looks exactly like the alphas parser we just saw. But in this case, we're also accepting like white space around the digits. So here's a function that takes out the white space. I mean, a parser that takes out the white space by parsing white space, digits, and more white space, just digits and white space, and so on. And we compile that as we did before using the compile function and a string to bytes, and it outputs the numbers. But again, we don't actually care about the output of the parser. We just care that it actually parsed. So here I have a function called numberString_p, which checks that some string is actually readable as a number. It does almost exactly the same thing as the parses function that we saw a couple of slides ago. It returns a true if it parses correctly. It returns a false if it fails. But the difference and the most important thing here is that you have this declare statement down here, which basically says, but notice all of this code was dynamic, by the way. There's no type signatures on any of this. This is saying that take some function from dynamic code and just go ahead and give it that type. Don't worry about it. I got this. Just go ahead and give it that type. So when the type checker when you turn type checking on and it encounters this function numberString_p, it'll say, okay, user, you've told me that it's of type string going to Boolean. I will just believe you and just go with that. So this is either awesome or terrifying or both.
Do you have a contract checking variant of that?
I don't think so.
Okay.
So the final rule of positive number takes this numberString_p that we just created as a guard, which is now allowable inside of the type-checked environment because we've declared it so, and then output something of type readable number. So the same way we did make positive number, we can go make readable, which takes a string and outputs a readable string because it has that guard form sitting right there. And at this point, everything along the chain is type-checked. So this is a trivial example of the type system. And most of you are like, hey, why didn't you just go parse int and catch the exception? Like, I get that. But the reason I'm showing you this is because I wanted to show you a less trivial use of the actual Shen type system, which is to actually give you strongly typed JSON. So where I work, we talk back and forth in JSON. The client talks to the server in JSON, and the server talks to the client back in JSON. It's nice because it's, there's some kind of like, you're not doing anything janky, but at the same time, we end up having to recreate code twice, once on the Ruby side, once on the JavaScript side, both parsing the same JSON, and if something goes out of sync, like a key, then everything goes to hell, and it takes a while to figure out. So what I want is strongly typed JSON, and not just any strongly typed JSON, I want a white list of keys that have turned into types. So what I mean by that is this. So given this JSON over here, imagine that it's converted to this internal Shen representation on the right. So it's a one-to-one conversion. Key values are represented as pairs. So now what I actually want is under type checking, I want this internal representation to type check as the type on the right. So notice that all of the keys, the string keys, have turned into types. So like look at this last phone number type, this last phone number. So here we have a pair of phone, the string phone and the phone number has turned into the key value pair of the type phone and a list of numbers. So what I actually want is when I look at the type of a function, I want to know exactly what the structure of JSON that it takes without me having to go figure it out and look at the actual code of the function. And so the exercise is now turning that JSON, that internal representation of JSON, into a type. And Shen is not a dependently typed language. So this would be like duck soup and sort of a dependently typed language. So we have to use like metaprogramming and macros to make this happen, but it will sort of show you a lot of what Shen can do. So the first thing we need to do, actually, if we're going to turn this form into a type, is iterate over everything inside of the object. So basically iterate over all the pairs at the type level. The way we do that is using this data type called object iterator. So the first thing we're looking at is the thing underneath the bar. So we're pattern matching on an object, on a list where the head is object, and XS is pattern matched on the rest of the list. And we're saying that the type of that is object and whatever KVS is. So what is KVS? So for that, we need to look above the bar. The first thing we do is take all of the things that are after object, and we separate them using the separate function, which is a value level function. You can mix type and value level functions in Shen. So separate takes, like if you had an object of A, B, and C, the data type matches on A, B, and C, and separate takes that and turns it into this comma separated list down here with A, comma, B, comma, and C. That's what it does. And by the way, the comma is just a symbol. All we're doing is marking that this list came from the JSON object type. So once we do that, we can actually have a data type rule that pattern matches on something, comma, and more stuff. So if I have something, comma, then we figure out what the type of that something is, and we put the rest of the stuff as a nested type inside of that, and the same with when I get to the end. So if I have an object of A, B, and C, the actual type is going to end up being A, open parentheses, the type of A, open parentheses, inside of that, the type of B, and open parentheses, inside of that, the type of C. So, by the way, if you haven't figured it out already, the A type, the B type, and the C type will correspond to the key value pairs in the JSON. So, the first thing we do is we wrap up the pairs into another type so that this rule doesn't fire on all pairs. So what we do is if we see KVX, it is of type KV and the type of the inner pair. So all we're doing is, so if we have a KV and a pair hello 1, it type checks to KV string number. So what we actually want now is that now that we have the object iterator and now that we have a way of wrapping up all of the pairs, we actually want to type check these strings into actual symbols. So forget all of the other keys for now, just stick with user, the user key. So what we actually want is for the user key, we want to generate a fresh data type for the user key. And what this is saying is that if I have a guard on some function that checks to see that user is the first thing inside of that tuple, the string user is the first thing inside of that tuple, and if that thing is of type string star and some other type B, then insert into the list of assumptions required for some proof P that this thing is actually of type user star B. And so what that means is, in order for me to convert a string of star A into a KV user star A, all I need is to wrap it up in this KV and have that guard that checks to see that user is the first thing in that tuple. And what I want is to generate this for all of the keys that we wish to pass around. So for that, we need metaprogramming. So first things first, we have a couple of helper functions. The first function makes a key type. So like when we're generating the user type over there, this is all this function does. It takes a key, say it's user, and outputs user-type. For the maker, which is this make function over here, it just outputs make-whatever it is that you pass in, user. So we're just generating strings at this point. So the first thing that we do is we generate this data type right here. And that data type corresponds exactly to this data type up here, except for the fact that all of the round brackets have become square brackets. And square brackets in Shen means don't evaluate me. This is just a list. This is equivalent to, I think, quoting in Lisp, right? Which means don't evaluate this list. It's just a list. So we turn all the round brackets into square brackets, which means don't evaluate me. And then we pass that into eval, which then proceeds to evaluate it. So we're building up an abstract syntax tree, and then we're evaluating it. So here we're generating the type based on the key that was passed in and the name of the type that we generated. We do the same thing for the function. So this function definition over here corresponds exactly to this function, not including the type signature, definition over here. So, but there is one piece of awkwardness. It's this cons form. It's unfortunately awkward. This is just Shen's way of saying splice that list in and don't evaluate it. So keep it a list. So remember, we had to keep that a list and not evaluate it. So here we're saying the square bracket, just keep it a square bracket. Don't turn it into a round bracket when you evaluate it. And finally, we declare using that declaration that we used before to just say that this function that we're making is of type string star a going to kv and whatever key that is, star a. So at this point, when we run through these functions, so for example, take the original object we were trying to type check up there, and here we have a whitelist of keys. So there's auth, user, pass, first, last, and phone. We map them all through register key, which then goes ahead and generates those data types and those functions for each one of those keys. So we're not quite done yet, right? We have an object that we need to translate. So we have an object that we need to translate, and in order to translate it, we can't just type in that original object in a bunch of pairs. We have to type in object, and we have to use this make auth thing because this thing is like an auth key, and this make user thing because that thing is a user key, in order to convince the type checker that this is of that type. And in order to do that, we basically need to rewrite the top thing into the bottom thing, and that's exactly a macro. So this is how Shen macros work. Okay. So Shen macros are different than macros that I've seen in any other Lisp because they don't work the same. And they don't work the same because when you define a macro, you're actually hacking the reader. Shen doesn't have the concept of reader because you're always hacking the reader when you define a macro. So say you have this def macro, my awesome object macro. So in all other Lisps, if you wanted to invoke that macro, you would go open parentheses, my awesome object macro, and the stuff that you wanted to rewrite. You don't do that in Shen. In Shen, all that means is that whatever patterns appear inside of that macro, so for instance, object, macro, and whatever else, that is what you rewrite. So the advantage of this system is that you can actually do like infix operations. So basically, you can have a macro that says, if I see plus xy, just rewrite, if I see x plus y, then just rewrite that to plus xy, right? So that you're actually hacking on the reader every time you create a macro. You just don't know it, which is why it looks different. So in order for me to actually invoke this macro, I have to go obj macro, and then the list of things that I want to actually create the macro out of. So the first thing we do is we use this awkward looking cons form thing in order to splice the list back in. We have object at the head, and then we iterate over the rest of the pairs using this function over here, which when it sees a pair, will call that keymaker function on that symbol. So if it sees user, keymaker x will be make user, right? And it will just go ahead and splice that in and continue iterating over the rest of the stuff inside of that macro, inside of that form. So, given obj macro and this big thing over here, it will actually, under type checking, will resolve to this type over here. And so at this point, you can pass that guy into a function that accepts something of this type. So, is there any further work that needs to be done? Sure there is. Like, what about equality? So, for instance, this type system does not, so if you have a JSON type of key A and key B, and you want to pass it into a function that accepts key B and key A, you're out of luck with this type system over here, which is kind of a big deal. And also, we have a regression bug with the internal representation because you can now legitimately have two keys that are the same using this type system. So I can have two key A, two pairs with A inside of it, and the type system won't complain. So there's definitely still work to be done, but it's amazing that you can get this far. And so would be nice to have some subtyping, maybe, and would be nice to have possibly even have row polymorphism, something like that. So I've just, yeah.
Can you go back to your macros and show how you do or don't handle hygiene in your definition. How do you know what is a constant or what is a variable in const object pairs or in obj macro? Or,
Oh, what do you mean constant or variable?
Shen's macros are non-hygienic, right?
Yes,
yes.
they are non-hygienic.
Okay.
So there are, in the actual code that generates the sample, there's a whole bunch of gen sims
Okay.
that just generate symbols for things that you don't want to like pollute the namespace or whatever.
Okay.
So I didn't show you that because I didn't want to show you guys a bunch of gen sims. Any case, good question though. I'm sorry. So equality, subtyping, row polymorphism. Just to show you how easy this thing is, I've just gone ahead and like implemented equality for you. So we can add another rule to object iterator. What this rule is saying is that if in the list of assumptions that you have, when you're if in the list of assumptions, in order to prove that y is of type object A, you have another object of type object B, then go ahead and take that B over there and make sure it has the same keys as A. And how do we do that? Well, we grab all the keys from A using this let up here on the top of the bar. We grab all the keys from B. We make sure that the length of the keys is the same, like there's the same number of keys in both objects. And then we make sure that they have all the same keys. And making sure it has all the same keys is trivial. It's just a simple function that pattern matches on the list and makes sure that the element of the list is present in the other list. And that's it. That's all there is to it. That's how equality works. So if we have a function that takes an object of type key A star number and key B star number, and we want to output something of type key B star number and key A star number, and we're just outputting the object back out, we're just taking it and outputting it back out, it works because of this definition right here. So this is how easy it was just to get simple JSON equality. Can I get subtyping out of this? Sure I can. Just check and see that I guess the first object's keys are available in the second object, and that's it. Not check and see that they're the same length, you know? Row polymorphism probably take a little more work. So the point of this is not to show that the Shen type system is the end-all be-all. It's just that type systems can be extremely flexible. And most type systems that we've encountered so far have been extremely rigid, including type systems like Haskell and OCaml and things like that. So Shen has really opened up my eyes to the fact that you can actually have a type system that sort of bends to your will as opposed to you taking something that somebody else has made and just working with that. Here are some resources to learn more about Shen. There's the Shen website. There's actually 3 editions of a book called the book. There's actually 2 editions of the Book of Shen. There's also the Book of Shai before. And there's the Shen Google group. That's really all I had, unless there was any questions. Yes, sorry.
So I haven't done Lisp in a long time. So,
Yeah.
In the absence of any extra rules that you provided, like you just did, is equality strictly structural? I mean, does it even know 1 + 1 = 2, or do you have to?
No, you pretty much have to tell it.
Okay.
Like, there's no like solver or anything in there that like does any kind of like solving at the type level. You just have to tell it that. Yes.
Does macro system have something like ellipses for this and any number of them, 0 or more of the following?
So is that the same as, I don't understand what ellipses are, but is that sort of the same as when I pattern matched an object, the rest of the stuff inside of that object form went into that pairs wildcard up there?
Yes, but I'm used to macro systems that I work with be able to inject, like via a macro, rewrite something and stick something at the very end of a S expression without having to iterate through the back.
I don't know the answer to that. Sorry. Yeah.
You mentioned that runtime, like user level functions, could be accessible in the type system.
Yes.
Can you talk a little bit about how that works?
The question was, I talked about user level functions being accessible at the type level, and he wants to know how that works. So basically just call it. So at the type level, they're operating on types. You're just passing in a bunch of symbols, and they're operating on those symbols. At the user level, they're also operating on the same symbols that are passed in via some other mechanism. It just depends on who's feeding the function, right? So the type level could be feeding the function, or something the user did could be feeding the function. They're just operating on symbols.
Oh, this is like runtime type verification, or is it static? Like,
It's static. This is static. Shen also has runtime type verification because there's no such thing as type erasure or anything like that in Shen. All types are accessible all the time. They're just symbols. But the type checker can run a user level function if it can give it the right symbols, right? If the type checker can give it a list and there's a function that accepts a list and does something with it, there's nothing stopping the type checker from handing that list off to that user level function. Like for instance, right here, the same keys, right? So all this, I'm generating a list using this KB list, the implementation I haven't shown you. It's actually kind of trivial. Just didn't want to take up the space. And since that's just a list, I can just pass it to that function that's accepting a list. So I think the question might be, can you do arbitrary I/O in the Shen type system? And the answer is yes. You can do anything you want in the Shen type system. You can launch missiles in the type. You can do whatever you want in the type system.
But is it a good idea?
I don't know. Maybe you do want to launch missiles. This is a Lisp. This is not Haskell. Like, I'm a huge fan of Haskell, by the way. Like, but that's not what this is. Yeah.
So since Shen is, I guess, a hosted language, would that be a fair description?
Yeah.
I mean, what's the interop like? What's the interop story like?
The interop story is exactly like whatever the guy who ported it makes it to be.
Okay. So there's not, the spec doesn't.
Yeah, the spec does not have an FFI, and I think that's a very good decision on the part of the spec, only because it's meant to be portable to any platform, and if whatever FFI that you put into the spec almost always depends on the semantics of the underlying platform, and if you let the porters just decide what that is, then you have a lot more flexibility, in my opinion. Yes?
I had a related question about about different hosts. Is there anything tricky you've got to implement? I mean, does it have call CC or anything that's going to make it hard to?
No. So the short answer is no. Yes, that's a good question. So in that list of 45 primitive functions that you need to implement, in order to like port Shen to your platform, is one of them solve the halting problem? No. The answer is no. They're all like pretty boilerplate looking functions. Yeah.
You have anyone using Shen in production?
No. Or who knows? Maybe it's a secret weapon behind closed doors. I don't know. I have no, but the answer is no. I don't know the answer to that. I haven't heard of any.
Has it inspired you enough to want to use it in production?
It's inspired me enough. I don't know if it's inspired my boss enough to want to use it in production. So yeah. So the problem is the JavaScript port is still not quite mature. It still generates bloated JavaScript. The Ruby port is slightly better, but it takes a while to start up when it's interpreting all the Shen. So there is still work to be done in order to make sure that the Shen ports are good. The only good port right now that I would use for actual production work is the SBCL port, which is what the author originally wrote. So there's that. But they both work. They're both correct ports as far as I can tell, the JavaScript and the Ruby. They're just not quite performant yet.
So now that your day job has turned you into a JavaScript expert, you could improve the JavaScript port.
It's on my to-do list, yeah.
Just making sure you are aware.
Yeah.
Does the JavaScript port port require is it self-hosting, or do you actually have to have a server component to do the compiling of the script?
So the JavaScript port, as it stands right now, actually requires Node in order to take some Shen code and output some JavaScript code, and then you include that JavaScript code inside of your index.html or whatever, and that's what gets interpreted.
That could run in the browser, though, just be really slow.
Yep. Yeah. That's right. Okay. Thank you very much.